Now, let us define the two new concepts. The first one is called moment, and the other is called variance. So the kth moment of a random variable x is simply the expected value of x to the power k. So the first moment is expected of x, the second moment is expected of x squared, and so on and so forth. Now, related to the second moment, we have the concept of variance. So the variance of x here is defined as, so we have this notation VARX for the variance of x. It is defined as the expected value of the square of the random variable x minus expected of x. So it is like for each outcome, we find out its value deducted by the expected value of x, and then take the square, and then we weight this value over all the possible outcomes and take the average. So in that case, we have this term. But then there is an alternative or equivalent definition. So the variance of x is equal to expected of the value of x squared, so this is the second moment, minus the square of expected of x, so this is minus the square of the first moment. We will get back to this a little bit later, why these two are the same. And then in real life, for convenience, we will also define a term called standard deviation of x. So the standard deviation of x is equal to the square root of the variance of x. Usually, the standard deviation of x is compared with expected of x. The reason why we want to have this one is expected of x should not be compared directly to variance of x. For instance, suppose that we are talking about the height of the students in a class, so expected of x is the average height. But for variance of x, it is going to be expected of x squared, something like this minus this one. So the unit is different. One is height, so let's say it is meter, and the other, the variance, the unit will be meter square. So in order to compare the variance with the expected value, we should not do so directly. Instead, we are creating the term standard deviation, which is the square root of it, get back to from meter square to meter in this example, so that we can have some reasonable comparison. All of these things, moments, variance or standard deviation, and also the expected value of x, they are usually called the statistics of the random variable x. So we first of all, we do not have the full probability distribution when we are talking about these values, because all of these are related to the expected value. So it is like some constant, but it depends on the original distribution. And now the good thing here is that we can sometimes make good deduction just simply based on these values, rather than we need to have the whole distribution, whole probability distribution of x. So in this course, we are going to rely heavily on the expectation, the variance, or even later about the moments of x to have some deduction on the behavior of x. Okay, so let's get back to the definitions of variance of x. We see that there are alternative definitions. We show that they are actually the same. So this is from the first part. So this is expected of x minus ex whole square. Now in the middle part, we just use algebra to expand it. So x minus ex squared is equal to x squared minus 2 times ex multiplied by x. Yeah, this is minus ex, okay? And then plus ex squared. And by linearity of expectation, we can further change this to expected of x squared. So this coming from the first term. And how about the second one? The second one is, we see that minus 2ex, this term itself is a constant. So in that case, by linearity of expectation, we can take this out. So it is minus 2ex multiplied by the expected value of this term. So multiplied by ex. And finally, for the last term, this is expected x squared. But then expected x squared itself is a constant. because this is the average value. Average value is a constant. The square of an average value is, of course, another constant. So no matter what happens, constant never change. So the expected x squared is equal to expected x squared. And we see that here we have minus 2ex times ex, and finally we have ex times ex. So after simplification, we will have just minus one copy of ex times ex. So that gives our alternative definition here. Okay. Okay, now let us check, okay, whether we have something like linearity of variance, as if we have linearity of expectation before. So recall that for any random variables x and y, expected value of x plus y, no matter what are the relationship between these x and y, we can write the expectation as equal to expected x plus expected y. So we wonder now, this is another kind of things that we have just defined. So is it true that the variance of x plus y is equal to the variance of x plus the variance of y? Now the answer here is, in general, this is not true. This is no. Okay, so we do not have linearity of variance. Okay, the reason here is that, okay, we have some extra term called covariance involved. So let me define what is meant by the covariance of random variables x and y. Now the covariance of x and y is defined as the expected value of x minus ex multiplied by y minus ey. Okay, and again, we have an alternative definition. So this is expected value of xy minus expected x, expected y. So first of all, from the formula, we see that covariance of xy is the same as covariance of yx. And actually, covariance of xy, you can treat this formula as a definition of variance of x as well. The variance of x is actually the covariance of x with x itself, right? If we plug in the value of y to be x, then this is x minus ex, and this is x squared, this is ex times ex. So you can use either definition to your convenience, and why this is equal to this one, yeah, we can prove it in a similar way as before. Okay, now the covariance will explain why we have, to explain why we do not have linearity of variance. So this is the theorem. Variance of x plus y is equal to variance of x plus the variance of y plus, this is the extra term, 2 times the covariance of xy. Okay, so let's see why this theorem is true. Okay, so for convenience, let us define two terms, a and b. A is x minus ex and b is y minus ey. Now we compute variance of x plus y using the definition. So this is the first definition. So it's equal to the expected value of the random variable x plus y minus the expected value of this random variable, this term square. Okay, now if you look closely of this middle part, because by linearity of expectation, ex plus y is equal to ex plus ey. So here, the middle part here, this graded area, okay, this gray shaded area is equal to x plus y minus ex minus ey. So if we rewrite it using a and b, so it is simply a plus b. Okay, now we have this gray part changed to a plus b. So we are now asking what is the expected value of a plus b all square. So using algebra and linearity of expectation, this will be expected of a square plus expected of b square plus 2 times expected of ab. So a plus b is whole square is a square plus b square plus 2ab. So we get this equality by linearity of expectation and simple algebra. Now expected of a squared, by definition, this is variance of x. expected of b squared by definition, this is variance of y, and expected of ab by definition, this is covariance of xy. So we get our theorem proven. Okay, so we can generalize the theorem for more random variables. Let's consider we have random variables x1, x2 up to xk. We say that, or we claim that, the variance of the summation of these random variables is equal to the summation of individual variance. Okay, so variance of all is equal to sum of all variance. Okay, plus this term. There is a term 2 times the summation of all pairwise covariance xi and xj with I less than j. So this is actually easily proven. Okay, the proof is similar as we just used before. Instead of defining a and b, we now define aj to be equal to xj minus exj. So by using simple algebra and also linearity of expectation, we get this one. Okay, so now we see that in general, we do not have linearity of variance. It is simply because there is an extra term involved here. So if this term is gone, then we will still have linearity of variance. So we give one condition when this covariance could be gone. It could be equal to 0. Okay, so this is the case when we are talking about independent random variables. Okay, recall that independent random variables is that whatever information about x that I give it to you, it will not change the view of what you expect of y. So you do not have, so any information about x will not give you any information about y. So suppose that we have independent random variables. Then expected of xy will then be equal to expected of x times expected of y. Immediately, for independent random variables, then the covariance will be equal to 0, because covariance is equal to exy minus ex times ey. So if they are independent, covariance is 0. Now notice that this is like one direction. It is not an if and only if condition. So covariance is 0 doesn't mean that the two random variables are independent. But on the other hand, independent random variables will make covariance to be 0. Okay, so this is only one way. Okay, so let's prove this one. So y independence implies exy is equal to ex times ey. Okay, so we go by the definition. So exy is simply all the possible cases of x and y can take on. Let's say x is equal to a, y is equal to b. In that case, we will have a value of a times b for x times y, weighted by the probability of this occurring. So expected of xy is equal to summation a, summation b, ab times the corresponding probability that x is equal to a and y is equal to b. Now, the good thing here about independent random variable is that the probability of x is equal to a intersect y is equal to b is the same as the probability of x is equal to a times the probability of y is equal to b. Now, after having this equality, we can now rearrange the terms a little bit, because the second summation is about b. So we can take all the things that is independent of b outside. So we will get summation of a times probability of x is equal to a, this one, multiplied by the summation of b times the probability that y is equal to b. Now the first part is simply expected of x. The second part is simply expected of y. So in that sense, we have proven that for random variables x and y, if they are independent, then exy is equal to ex times ey. Okay, so now we have immediate corollaries to obtain. So for independent random variables xy such that they are independent, their covariance is equal to 0. So we will have linearity of variance. And similarly, if x1, x2, xk are pairwise independent, so the corresponding covariance terms will all be 0. So again, we will have linearity of variance in this situation. Now, notice one important thing here is that we just need pairwise independent. We don't need mutual independence. Pairwise independence is easier to obtain, easier to achieve than mutual independence. Okay, so that's all for lecture 7. Thank you.